Hi kids. So this one's going to be a long one, but there's absolutely, I don't need these, absolutely zero worksheets. Let me go close my door real quick. I'll be right back. Okay, I'm back. So today's lesson is going to start off with gravity and then move on to centripetal acceleration, centripetal force, projectiles, all today. And as you can see, gravity is a really big deal. Alrighty then, moving on. Gravity is. Again, if you couldn't print off the note sheets, that's fine. Just go ahead and write this down on your own piece of paper. Pause as much as you need to catch up. Go back as much as you need to. It's all good. Gravity is an attractive force between all objects. Okay, that's the main definition. There's also something else I want you to know about it. You don't have to write this second bullet down. It is one of the four basic forces of the universe. Already taught you strong force in the nucleus. You know about electromagnetic force because I think, yes, I did. I played with that static electricity in class a little bit, didn't I? Yeah. The weak nuclear force, which we don't go over in physical science, and gravity. All right. Also, gravity is dependent upon the masses of the objects and distances between them. Don't have to write that down because it's in the next little thing. That next little thing is the law of universal gravitation. I thought that wouldn't be up there yet. Oh well, it's there. So this is an equation, a formula, which you will not have to ever use to solve for anything, but you do have to look at it and learn about it. So here it is. This is the law of gravity. I showed you this before. I talked about different types of models. This is the mathematical model for gravity, how it works. F sub g is the force due to gravity. We also call that weight. Equals big G, the gravitational constant of the universe, which is this ugly number down here. I'm not going to make you use it, just let you know it's there. It's a tiny number because it's times 10 to the negative 11th, whatever. The part you have to worry about is this fraction here. Mass of one object, mass of another object, over the distance between them squared. It's not the distance from the surface of one to the surface of the other. It's the distance from the center of one to the center of the other. So when we're talking about your weight, we plug in your numbers here. The distance between you and the Earth is not 0. It's a few thousand kilometers because it's from your center, which is somewhere behind your belly button, down to the center of the Earth. That's the D. Stop laughing. Alright. Because it's a fraction, you have written all your notes, you can look at it. Mass and gravity are directly proportional. Mass is the numerator, the top. If I increase the mass of any of the objects, either the planet you're on or you, the weight, the F sub g, changes. Gets bigger. More mass, more weight. Less mass, less weight. Make sense? Good. Distance and gravity are inversely proportional. The further away you get from something, the less it weighs. Further you get from the Earth, the less you weigh. Technically, you weigh less on top of a mountain than you would down at the bottom of a valley because you're a little bit further from the center of the Earth. Your typical bathroom scale wouldn't pick that difference up, but it does exist. So if you want to lose weight, climb. Anyways, I'm not going to worry about this part. If we're in class, I have to do it, but we're not taking a final right now, so boop-a-doop-a-doop-a-doop, don't care about that. If you want to pause and read it, go back and pause and read it. All right, next concept is weight. And the definition of weight is the gravitational force exerted on an object. Sorry, I had to wet my whistle there. All right, follow this logic. I know, logic. You can handle it, though. Weight is force exerted by gravity. That's the definition. So far, so good. Force is measured in newtons, which you should know by now. Therefore, weight must be measured in newtons. The unit for weight is newtons in science. I know you don't use newtons at home. You use pounds. We used to pounds. We know what pounds mean, but oh well. In science, we use newtons. Also, the equation F equals ma can be used to figure out your weights. I'm going to show you what we mean here. Put F subscript g instead of just force. So it's force due to gravity. Whoops, what the heck? Which is the weight. Mass is the mass of the object you're weighing in kilograms. Mass is always in kilograms. And the A becomes acceleration due to Earth's gravity, also known as lowercase g. If you still have your reference tables, it's on the front and the numbers there for you. So now you have F subscript g equals m times g. Weight equals mass times gravitational acceleration. On Earth, the value of g is always going to be 9.8 meters per second squared. Okay. All objects accelerate downward due to gravity on Earth at that rate, 9.8 meters per second squared. I don't care if you drop an elephant or an ant out of an airplane. They're going to accelerate 9.8 meters per second squared. Air resistance will pretty quickly stop the ant from accelerating, but gravity is still trying to make it. All objects do that. You don't believe me? See, if we were in class, I'd be taking you outside to the football stadium with a bowling ball and a softball, and two of you would climb to the top, the rest of us would get away from the bottom, so you couldn't hit us in the head, and you drop them both on the same height at the same time. They'd both hit the ground at the same time, even though one is way heavier than the other. Mass doesn't matter. I forget if it was Galileo or Newton that did this experiment. He made all these balls, quit laughing, of the same size but different masses because they're made out of different substances. Balsa wood, silver, iron, steel, plaster, whatever. Took them up to the same height and dropped them and timed how long it took them to fall. And they all felt the same rate. He made them all the same size and shape because he couldn't eliminate air resistance, but he could make it a constant in his experiment. There you go. Alright, sorry I'm not at school, so I can't prove it to you, but still. Next thing you note is weightlessness. If you need a break, by the way, you can always pause, go get a coffee or whatever, and then come back to this. You know, you ain't got to stay here through the whole thing. You're free. You gotta go pee, you ain't got to raise your hand and ask. Go pee. True weightlessness is defined as the condition where no gravity acts on you. You write that down. And realize that never happens. You're never truly weightless. You can feel weightless, but you're never truly weightless. The answer to this question is no. They're falling. They just don't feel it. I'll explain how they're falling in a minute. They're in a state known as free fall. So that's the next thing on your notes. Let's define free fall. Free fall is defined as a condition in which the only force acting on you is gravity. Pause, write it down, coming back. Alright. When you're in free fall, you cannot feel the gravity on you because it's not pulling you down into anything. Right now you feel, I'm feeling the gravity through my butt because I've been sitting on this chair for hours. I got up a few times, but yeah, I need to get up and walk around some more. We all do, I think. Whatever you're sitting or laying upon, you're feeling the gravity because you're feeling it pull you down into that object, and that object pushes back up on you. You feel that pressure. What if I take the bed or the chair or whatever out from underneath you? You'll fall. While you're falling, you don't feel any gravity. That weightlessness really messes with your senses. There's a ride at the county fair that does that. I forget what it's called. It's a big square thing. There's rows of seats on all four sides. And you sit down, you buckle up, and it goes up, 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 then drops you. While it's dropping you, the chair is falling out from underneath you. You don't feel yourself being pushed into it as hard. You feel weightless. You're not weightless, but it's that feeling of weightlessness. You're in free fall because the chair's in free fall with you. The astronauts are in the International Space Station going around the Earth. In orbit, they're actually falling around the Earth. More details coming up, but they're falling around the Earth. Alrighty. Projectiles are also in free fall. A projectile is anything thrown or shot through the air. Projectiles are actually moving in two directions at the same time, both horizontally and vertically at the same time. This picture coming up is also on your notes. Now I got it color-coded here, yours is black and white, so here we go. The top path, the blue cannonball, is what would happen if this cannon shot the cannonball and there was no gravity, the gravity-free path. Notice how all of these are the same distance apart from each other. This is 0 times 0, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds later. Why are they all the same distance? Because it's traveling at a constant speed or velocity. Alright? I'm ignoring air resistance to make my life easier, and yours too. Alright, so constant speed, not falling, no gravity, just gonna go straight line forever. This path represents what happens if you just drop the cannonball from that same height. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds later. Why are those 5 at different heights? Why is that? Because of acceleration. Gravity is accelerating these. So this one cannonball. So each second is going a little bit faster. Acceleration means it's increasing speed in this case. So it gets only this far in 1 second, but as it's falling, it goes faster, so it gets further the second, even further the third second, the fourth second, the fifth second, till it hits the ground. Whereas this right here is a gravity-free path, all the same distance, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. The cannonball has to do both types of motion at the same time. It's being given this horizontal velocity by the cannon, and it's being made to fall at an accelerating rate by gravity. So it does the red path. It's doing both at the same time, trying to keep a constant horizontal velocity while it has an increasing vertical velocity downwards. Boom. Till it hits the ground, and something else happens to stop it. No, that's nice. Alright. Projectiles follow a curved path as two directions of motion act at the same time on the same object. You can even throw it up in the air. If you give it a little bit of forward oomph too, it follows a curved path. Gravity slows it down till at one point it has zero vertical velocity, still going sideways, but nothing up and down, and then it starts coming back down again because of gravity. Alright, if we were in the room, I'd throw a piece of paper up in the air and get y'all to get it better, but I'm not there with you, so sorry. Weird thing, whether you throw or drop a ball that is always accelerating downwards at the same rate, 9.8 meters per second. Which means, and again, I have a cool toy for this in the classroom, but I'm not in the classroom. I didn't bring it home with me, so I can't do a recording of it, so sorry. If you throw a ball perfectly horizontally, and at the same time drop another ball from the same height, they'll both hit the ground at the same time. You gotta shoot that one ball perfectly horizontally. If you shoot it up, it takes time for that upwards part of the velocity to get eaten up by gravity before it starts falling. If you shoot it downwards, it's gonna hit the ground faster. You gotta shoot perfectly horizontally and drop another one from the same height at the same time. Hard to do at home, but if you can do it, try. It's awesome. Here's a picture of that happening. This is taken with a strobe light. Strobe light flashing multiple times every second. So you see this one was shot off horizontally, this one was dropped. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Flash of the strobe light. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another one in there you can barely see because of the glare. 11 and then 12. At each flash of the strobe light, the balls are at the same height. The yellow ball is falling just as fast as the red ball, which just happens to be going sideways at the same time. Alrighty then. When something is moving in a curved path, the direction of acceleration is always to point to the center of the curved path. That is called centripetal acceleration. So the definition of centripetal acceleration is acceleration towards the center of a curved path. Write that down, pause, write it down, come back. Welcome back. Accelerations are caused by forces. Always, always, always caused by a force. Any force causing a centripetal acceleration is a centripetal force. It can be anything. You tie a ball to a string, and paper ball to a string, and you swirl in the air over your head. The tension in the string is a centripetal force. causing that ball to travel in a curved path and accelerate towards the center of the curved path. The moon going around the Earth, gravity is what holds it in. It keeps it from flying off into space. Gravity is a centripetal force in that case. Centripetal forces are always pointed to the center of the curved path. Alrighty then, so that centripetal stuff is on the second sheet of notes. There's some other pictures I want to look at too, so let me exit this. There we go. Let me pull up the notes and drag it over to where I'm recording. There we go, and make it bigger. I want to talk about this. Newton's imaginary cannon is down here, but look what Newton was thinking about, alright? So Newton knew how cannons worked, and he hypothesized if you have a cannon that is strong enough and get it up high enough, you shoot a cannonball out of it, the curvature of the cannonball's path will match the curvature of the Earth. Well, if you're one of those flat earthers, you're wrong. Deal with it. Earth's curved. Earth is a big round ball. Yeah. Anyways, he hypothesized if you get the cannon strong enough, you get it up high enough, cannonball's curvature would match the curvature of the Earth and it would never hit the surface. He was right, but there's no such thing as a cannon strong enough to do it. You need rockets for that kind of thing. This is how we put things in orbit around the Earth. Technically, they're falling. They are projectiles. Gravity has them and they're falling, but the curvature of their projectile path matches the curvature of the Earth. And so they never hit the ground. To get that to happen, you really need to get above the atmosphere because air resistance will slow it down and make the curvature not match the curvature of the Earth anymore, and it'll hit the ground somewhere. You gotta get out of the atmosphere for that to happen. Cool. That's all I have for today. That's enough, I think. That is a 17-minute video. Hope you took a break in the middle of it. I've got one more day of instruction for you tomorrow. I'm going to give you some momentum stuff, and then that's it before spring break. When you come back from spring break, I'll throw an assessment at you, but give you all the time in the world to do it. You ain't got to do it that day. You can go back and review stuff, and then take it a couple days later. Whatever. I'm going to leave it open. All right? Don't slack off, but don't rush either. You got time. I know you got other classes too. All right? So, bye-bye.